what I'm going to talk about is basically ways to deal with noise and errors in the noisy intermediate scale quantum devices era. Okay, so what do I mean by what is meant by the NISQ era? You know, if you think about the number of qubits and the error or the infidelity of maybe 2 qubit gates, and then if you have enough qubits, more than say 1 million, and the error rates are low enough below some threshold. Say the threshold is 10 to the minus 3, but you need actually to go below that. So if your qubits are below that, if your qubits are better than some threshold,
sorry.
Now you owe me 2 more minutes. And you have enough of them, then you have a fault-tolerant quantum computer. But right now we're pretty far from that. We do have machines that have on the order of hundreds of qubits, but their noise, is not that low, maybe below 10 to the minus 2. So then the question is whether we have kind of an intermediate regime here where we have we have large enough devices, but we could not do error correction because we don't have large enough devices with low enough error rates, but not enough qubits to do error correction. And we could still somehow do some useful quantum computing. Okay, so it's a big question, I think, in the field of what is the power, computational power of this regime where fault tolerance is not possible, but we have large devices with pretty low error rates. Can we do something useful, meaning that something that has a quantum advantage in the sense that we cannot basically simulate this quantum computation on a classical device? Okay. So I'm not going to answer this question, but I'm basically going to discuss what's needed in order to basically make this regime possible. And in this regime, you cannot have, since you don't have this sort of automatic error correction, you need to actually do something else in order to reduce the errors. Okay, so I'm going to discuss this. So I'm going to have 2 lectures, and today I'm going to discuss about diagnosing noise, how to actually diagnose noise in an efficient way on large-scale devices. And then hopefully tomorrow we'll talk about how we could use that in order to suppress or cancel the noise in quantum computation without doing error correction. Okay. Okay. So so let's start with this. So diagnosing noise, it can have several benefits. Okay. So if I do a good diagnosis of the noise and the errors in the system, first thing I could do, I could improve the hardware. Maybe I could design a new chip, or I could identify that I have some kind of bottlenecks or certain faults that I could fix by just improving the hardware. Another thing I could do, I can improve the control. For example, I can improve the pulses that I send to a superconducting qubit device, or to an ion trap, or to atoms in an ion trap, in order to get higher fidelity gates. Okay? In order to do that, I need to actually know precisely what are the errors in the gates that I'm applying. And then the last thing I could do, and we'll discuss that tomorrow, is that once I have a very precise description of the noise, I can also do, let's call it recompilation of quantum circuits in order to cancel the noise in those quantum circuits kind of an algorithmic level. One example could be, if we have coherent noise, if noise is coherent, meaning it comes from some Hamiltonian, and I can diagnose it to a very good precision, I could completely reverse it, right? Because no information is lost from the system. And in principle, it's a reversible operation. I could try to completely reverse the errors. we know that many of the errors in quantum computers are actually not reversible. They actually cause to, information loss or even to increase of entropy. And then we'll have to pay some price in order to cancel those errors, and then we'll discuss this tomorrow. So today I want to focus on how to diagnose errors and how to diagnose them on large-scale devices, okay? So I'm going to start with some preliminaries. So the first thing I want to discuss, I know that you've already seen this. I just want to introduce some notations. So a quantum process. Okay, so we're going to describe a general quantum process using a Krauss decomposition. Okay, that's one way to write any quantum process. So this could be a gate or a noisy gate, okay, or just a noisy idle operation. Okay, and these Ki's are matrices with a constraint. Okay, so I think you've seen this in previous lectures. Okay, it's also useful. What? The opposite. Yes. So I should say this. I didn't bring a presentation. I prepared notes. I forgot them at home, and I reconstructed them on the cab right here. So, please try to spot any errors that you may find, okay? Okay, so another useful notation would be to basically note lambda. Let's call it in the Pauli basis, okay? So let's write the matrix lambda AB as 1 over 2 to the n. N is the number of qubits, times trace. I'll introduce all the notations in a second. So PA is any Pauli string on n qubits. Okay, so Pauli, that's why Pauli string on n qubits, and I'm including the Paulis, okay, and 1 qubits are identity, x, y, and z. Okay, so I'm also counting identity on single qubits. Okay, so when I write P, this is a string of Paulis acting on qubits. Okay? So you've seen this matrix before in the previous lectures, or no? Okay, so basically, the Paulis are a basis to all matrices, okay? And what I'm doing here, I'm basically asking, okay, this operation lambda, it takes this basis element to a superposition of basis elements, P's. And one thing to remember is that these P's are basically giving you an orthonormal basis or, orthogonal basis. So if I use this normalization, okay? So I get non-zero trace only if PA and PB are the same, okay? So PA, PB is delta AB, okay? So this gives me a matrix. It basically tells me what is the projection. I apply my lambda on my basis element, and I project it on PA, and this is basically the matrix lambda AB. Okay, so if I want to write my operation, okay, what my operation does to a basis element, PB, okay, I could write it, basis element PA. I am going to write it as sum over B, lambda AB, PP. Okay? So this is what this matrix does, represents. It basically represents how the quantum operation transforms the basis elements PA. Okay? Please ask me, if you have any questions, please stop me. Yes?
Can you explain what you mean by why you define these basis elements?
Because they're very useful, okay? Because they have this property, okay? So it's a very good basis to use for matrices, okay? That answers the question? Okay? Okay, we'll see in a second that there's a very, very useful basis to expand all our operators and super operators in. Okay? Other questions? Okay. So So these are quantum processes. I'm wondering what should I keep here. Never mind. Okay, so the next thing I want to, so now I want to, basically when I say diagnosing the noise, I want to basically know when I apply a gate in my, I have my quantum computer, I apply a gate. Okay, I want to know what is the quantum process that describes this gate, okay? I want to know this matrix lambda AB. If I know the matrix lambda AB corresponds to each gate, I know exactly what each gate is doing in the system, including all errors that are caused by applying this gate. It's a full description of what happens in the quantum computer when a gate is being applied. Okay, is that clear? So this lambda, when I discuss this lambda, you can think about this lambda as acting on the whole computer, okay, on all of the qubits. Okay? Each time I press a button and apply a gate, some process map is being acted on all of the qubits. And we want to know exactly what is this process map, because once we'll know it, we could do all the things I said before, okay, improve the hardware, etc. Okay? Okay, so now, how do we learn what is this process map? So the first and most elementary thing to do is something called quantum process tomography. Okay. Okay, so I want to do quantum process tomography. So what is quantum process tomography? I'm going to basically have a set of initial states, rho I. So rho i's are a set of initial states, okay? And each of these states, I'm going to write as the sum over rho I B or A, PA, okay? So each one of these states I can expand in this Pauli basis. It's a density matrix. You've seen this density matrices before? Okay? Okay. So each density matrix I could write in this Pauli basis. Okay? And then what do? I prepare a state, prepare rho I, okay? Apply the gate, okay? Apply lambda, I press the button. I first prepare the state rho I, press the button, apply a gate lambda, and then measure, okay? Let's measure the expectation value. After I've done this, let's measure expectation value of some observable, Pauli observable PB. Okay, so in order to measure this expectation value, I have to repeat this experiment many, many times in order to have this expectation value to a good accuracy. Okay, and then once I've obtained this to an accuracy which is good enough for me, okay, I'm going to write PB, okay? That's just trace of PB times lambda acting on rho I. Rho I is my initial state, okay? And this is going to be trace PB. Okay. Where's the eraser? I'm going to do this slowly for now. Okay, so trace PB, sum over A, and rho I A, lambda acting on PA. Okay, so far, I've just used the linearity of this process map. Okay? Yeah. Yes, P is a Pauli string, yes. No, it's a very good question. So what happens usually that there is a subset of the qubits that this lambda acts on. It could be quite a large set. Okay? So
it seems like a pessimistic assumption that it will go into the analysis and
no. Okay, so this is an excellent question, and keep that, for a bit later. And I'll explain why it's actually important to describe process map that actually act on the whole register. But let me just go through this math for a second, and then If I don't remember to ask you, please ask that question again, okay? Because it's a very important question, okay? Okay, so, okay. So then, you know, we already saw what we want to do here. And basically what we get out of this is we get lambda, sorry, let me put C here. Just, okay, lambda BA rho I A, okay? That's what happens when I plug the description of lambda, okay, acting on this. And sorry, sum over A. Yeah. If I don't write the sum, there is a p at the index, and I don't write the sum. I'm assuming there is a sum. Okay? So this is what happens when I measure the expectation value of PB. This is the relation between the expectation value I measure and the matrix lambda AB and my initial state. So now this gives me an equation. This is measured. Okay? I know what I prepared, or at least I think I know what I prepared. Okay? And these are my unknowns. I need enough equations. Okay, so I need to measure enough of these B's and prepare enough of these I's. So I have enough equations to solve for lambda AB. And once I do that, I have lambda AB and I'm happy. Okay? Yes. So that's a very good question. So there are two types of errors that are hard to disentangle from the lambda here. Okay? So first, you know, when I wrote this, I assumed that my measurement, I know exactly what I'm measuring. I'm measuring PB. And I assume that I know what is rho, what exactly I'm preparing. Okay? But in practice, the largest errors in quantum computers are actually the ones in the measurement. Okay? The measurement and preparation errors are the largest errors. They're larger than all the gate errors in today's quantum computers. In all architectures. We can discuss that. I'll discuss it in a bit, because you can have, you can diagnose spam errors, okay? But for now, trust me, okay? Okay, so the question that was asked here, so there's a notion of spam errors, spam, state preparation and measurement, okay? And this type of protocol is not robustly spam errors. It's hard to disentangle these type of errors from the actual lambda. So if I'm solving from some lambda, I'm assuming something on my preparation and measurement, okay? And it's hard to disentangle the errors from in the gate and the errors in the preparation and errors in the measurement, okay? That's one drawback of quantum process tomography. It's the fact that it's hard to disentangle those spam errors. There's another very big drawback to quantum process tomography. What do you think it is? Yeah? That's another big, there's two big drawbacks. One of them is that, you know, if I really want to diagnose lambda on a full device, I need to do a lot of measurements and a lot of preparation, okay? But suppose I know that some of my lambdas are zero, some elements are zero, so I could dilute this a little bit so I don't have to measure all of them, okay? But what is the other big drawback of this technique? So one is spam, yeah? No, these P's are, you can think about it, if I want to measure PB, okay, I would measure in the computational basis. And before I measure in the computational basis, I would apply single qubit Pauli's. Yes. So, right. Right. So when I measure, usually it's convenient to describe the measurement as applying single qubit rotations just before measuring in the computational basis, for example. And that would give me basically measurement of Pauli strings, okay? I could also measure more complicated observables, but I could basically write them at the decomposition of these P's. I can always write any more complicated observable as a sum of these P's. So if I know how to measure these P's, it's enough, okay? Yeah. No, look, I can fully diagnose this lambda. This lambda can have coherent parts, incoherent, everything is included in this lambda. It could be a unitary matrix, not unitary. All of the full description of the gate under an assumption that is called the Markovian assumption. I think you just already discussed this, so I will not repeat. All the information under the Markovian assumption is included in the description of this lambda. You don't need to know anything else, okay? So what is the second big drawback of this thing? You have to do you have to get a lot of statistics in order to get good accuracy. And this takes a lot of time, okay? So let's do an estimate of, suppose I want to actually measure my lambda. Okay, let's think about what accuracy do you think I want to measure my lambda? What accuracy, right, the elements of this matrix, to what accuracy do I need to know them in order to have useful information about the system? Better than 1%, for sure. Why better than 1%? The fidelity is around 1%. I don't know, say, which elements are big or small. So I want to have at least, 90% accuracy. Okay, so I would need to go to 10 to the minus 3 accuracy. Okay? How many times do I have to, how many repetitions to measure this expectation value? I have to repeat the experiment many times. I know you know the answer. So how many times do I have to, how many repetitions of the experiment do I have to do in order to measure this, the accuracy of 10 to the minus 3? Well, it's quantum shot noise, right? It's I have to measure 1 over square root. Then if I want the accuracy of epsilon, okay, the number of measurements I have to do is basically 1 over epsilon squared. Okay? So if I want accuracy, that's a very important thing to remember. This just comes from statistics. So for accuracy epsilon, the number of shots, I'll call it NS, so number of repetitions, okay? Number of experimental repetitions of the same thing. Apply rho I, measure PB, okay? So for each setting, so for each rho I and for each PB, I have to do 10 to the 6, about 1 million measurements, million repetitions, okay? Okay, so now let's think how much time it would take. So if it would take a lot of time. Okay, let's see. I can do this. So let's think about 2 qubits, okay? I have 2 qubits. Do this estimate, okay? And so on a superconducting device, the measurement and preparation time are the longest times. So it would take mostly around 300 milliseconds, microseconds, okay, to prepare and to measure, okay? So prepare, state preparation and measurement takes around 300 microseconds, okay? And how many elements do I have to measure? I want to know, it's 2-qubit operation. How many elements do I have in my lambda AB? 16 squared. Why? Because the index A, how many values does the index A take? 16. B also 16. So, right, so lambda AB is a 16 by 16 matrix. So 16 by 16 is around 300. Okay? Okay, so what? Yeah, no, of course they do, because each Pauli string is in the index here. And all of these Pauli strings are distinct. So each Pauli, right, each PA, it's sigma mu A on qubit 1, sigma mu B on qubit 2. Yeah, again, I need the number of elements I need to know in this matrix, okay? Each index has 16 values, so it's a 16 by 16 matrix, okay? Okay, so let's try to do this calculation. So we have, we need 10 to the 6 to get 1 element, okay? times around 300 times around, 3 times 10 to the, minus 4. Okay? So it's around to the 10 to the 5 seconds. So it's a couple of hours just to measure a 2-qubit gate. Okay? By the time you've obtained this information, that information is already not relevant because some fluctuation happened. Somebody turned on the microwave in the lab next door, and the value is, has changed. Okay? So it's a very long time to obtain this information. Okay? There's a question in all of these, in all of this business of what is the stability of the systems we're trying to diagnose? What is the stability of these parameters? Okay? So this is a very long time just to diagnose a single 2-qubit gate. Okay? To this accuracy. Okay, so far, what I said is clear? Okay, so anybody has an idea how to improve this?
Maybe we could try to listen only half of the power zeros, and then instead of dealing against channels that is uniform for all powers, your channel is uniform only instrument uniform only of the half of them, and then your code, your initial code, do not need actually to be fast against all zeros. So it might give you an suggestion.
Okay, let's say that I'm not that smart.
Okay.
And I just want to know all of these elements. Okay? So, no, what you said might be an interesting direction, but let me not be sophisticated. I need for some reason. My goal is to obtain all of these elements. Okay? But I want to do it quicker than 5 hours. Yeah. But look, I have 256 numbers I have to evaluate. Each one of them I need to evaluate with accuracy of 10 to the minus 3. I have no way around this. If I do this, there's no way around it. If I really want to know all the elements, unless I think that some elements are insignificant, as was also what you're saying, like in compressed sensing, I can assume that, that the matrix I'm dealing with has some sort of, sparse or something like that. No, I'm not doing it for now. Maybe later. For now, I want to know all of these elements. Yeah. What? No. What? Yeah. No, but you're getting warm. If you run the gate in inverse, but yeah. What? Yeah, but for now, let's think I have a device with 2 qubits. So. Yeah. Oh, yeah. Okay, it's not fair because he's my student, but yes, what I could do is I could do amplification. Okay, so let's think about what is amplification. This is a very important notion in all of this business of characterizing and diagnosing noise. So let's discuss what is amplification. Okay, so amplification says that, look, you want to know the noise. The noise is small, okay? It's around 1%, okay? So my signal is very small. That's why I needed a lot of shots, right? Because I needed to get a good statistical accuracy, which is smaller than the number I wanted to measure. But why don't we actually make the error bigger on purpose, okay? And then I have to measure a big signal. I can measure it with a smaller accuracy, with less shots, right? With the bigger error bar, okay? Because the signal will be big. How do I amplify? How do I make my error large? I just apply the operation many times, okay? So instead of what we had before, where we measured PB was, lambda, and I prepared row I and measured PB. Now let's apply lambda n times. Okay? Let's do an example here. I think it might help. Risk of completely running out of time. Okay, let's do an example. Should we do an example for this, or is it clear? Okay, let's do an example just for fun. Okay, let's think about the depolarizing map. Okay, depolarizing map, yes. Yeah, I repeat the same operation, but many times. Yeah, so I'm assuming, that's a very good question, that every time I press the button, I get exactly the same error. Okay? Yeah. Or the same distribution, same statistical distribution of errors. Yeah.
Are you assuming that lambda is unitary?
No. Yeah, I am going to do a depolarizing channel now. Okay, so it's manifestly a non-unitary operation. Okay, but it could be also unitary. It could be both. It could have a unitary and a non-unitary part. Okay. Okay. So let's first write the depolarizing channel. Okay, let's go back and write it like this. The depolarizing channel acting on density matrix rho. I'm going to write it as 1 minus p rho plus p over 3. Okay, this is a bit painful, but one. Okay. Now, if you go back to that matrix I wrote before, the matrix representation of lambda, okay, I would write it like this. It would basically be 1 lambda, lambda, lambda. Okay? It would be a diagonal matrix. What this diagonal matrix does, you remember this, I think, from previous lectures. You know, if I have rho, which is identity plus n dot sigma over 2, what it does is, so these lambdas, they just shrink the value of this vector n. So n is multiplied by lambda. Okay, so lambda on rho is basically 1 plus lambda n dot sigma, and n is smaller than 1. Okay? Okay, so now what happens when I apply lambda? What is the matrix representation of lambda to the power n? Right, it would be this to the power n. Okay? Now I go and I do tomography, okay, on this operation, which is lambda to the n. Okay? Okay, so, and then let's see. So again, let's assume I want to know lambda. Okay? My goal is to know lambda, and I want to use less shots than 10 to the 6. Okay? I'm assuming, say, lambda is small, around 1%. I want to use less shots than 10 to the 6. So I go ahead and I measure sigma z, observable sigma z, okay? And I prepare, let's also prepare, okay, sorry, let's prepare the state 1 plus sigma z over 2. This is just, you know, the state 0, okay? Measure sigma z, observable, okay? So sigma z would be trace sigma z 1 plus lambda to the n sigma z over 2 maybe, okay? Which would give me lambda to the n. That would be the trace, okay? Okay. So now let's compute how many shots I would need to do in order to basically learn, how many shots I need to do in order to learn lambda to some accuracy. Okay, we'll see that we need much less. Okay, everybody is with me? Understand what I'm doing? I want to measure lambda, so instead of applying this lambda once, I'm applying n times. And now the expectation value sigma z is not lambda, it's lambda to the n. Okay, so I've amplified the error. Instead of being lambda, right, the error is more or less lambda. But now I've amplified it. I caused the signal to be lambda to the n. It's true, but you'll see that I've amplified. Yes. Well, let's see in a second. It will be clear in a second. Okay. 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 So now let's assume that I measure. Okay, so now let's assume that I did NS shots. Okay, that means that my expectation value is the correct expectation value plus, plus some epsilon. Okay, this is the expectation value of sigma z. Okay, but I know that I've applied the operation n times, so I'm going to compute the lambda that I'm going to report from this. Okay, is going to be basically 1 over n log of sigma z, right? Because I know if I did infinite number of shots, right? If I did infinite number of shots, this would be log, sorry. Okay, so if I did infinite number of shots, this is the value I want to report, right? Log of lambda measured will be 1 over n times log of sigma z. So I take my measured value, take the log, divide by n, right? And that will be log of what I actually need to report. Okay? Yeah, we'll compute the optimal n in a second. Okay? So it's true that what Robert is saying, that I don't want n to be very, very large, because then I have no signal. This will go to 0, and I have noise, and I have statistical noise. So I cannot do this forever. I cannot take n equal to infinity, because then I'll have no information. So I have to stop after some optimal n. Let's compute that optimal n. Okay? Okay, so, right, so just to finish up on this, so if I do this, I'll get lambda plus 1 over n epsilon over lambda, sorry, log of 1 plus epsilon over lambda to the n. So it's approximately lambda plus 1 over n times epsilon over lambda to the n. Okay? Everybody happy with this calculation? Okay? This is log lambda, sorry. Okay, so basically what I measured is the correct value plus an error which now behaves as epsilon. Okay, epsilon is the 1 over the square root of the number of shots. Okay? But times 1 over n. This is the okay. So I've now reduced. If you disregard this, sorry for this abuse, naively I could say I've now reduced the error by a factor of 1 over n. Is this clear? Because I applied this n times, I've reduced the statistical error for a given number of shots from epsilon to epsilon over n. Okay? But there is a disclaimer here, because I cheated. I have to correct, I have to divide this by lambda to the n. Okay? So now I have to basically compute what is the optimal value of n to use. Okay, and we could do that. Just take the derivative of this function. Okay, this is a function. Take the derivative of this function. You'll find that the optimal n optimal is around 1 over log lambda. Okay, so for fidelity, say, of 1%, you'll want to go for 100 applications of lambda. Okay, if lambda is 9, so if lambda is 0.99, okay, you need to go around, you could go up to n of 100. That would be more or less your optimal n. Okay?
Question?
Yeah.
So let's assume for the moment that your noise is just a swap gate. Just swap it with your...
No, this is a very big noise. So
Okay,
here, yeah, I should have maybe said this.
When you just take the power of your noise, then lambda will be...
What I assumed is that when I did this analysis is that lambda is small. It's a very good question.
Okay. It's not... just that we want to assume that it's not...
During the lecture, we ask questions, not make a discussion.
We could discuss it later.
But the point is that I think it works with the assume that lambda is around...
The error is very small. Okay, so lambda here is close to 1. very close to 1. Okay? That's my assumption here. I'm trying to diagnose a small noise over an ideal operation. Okay? And then I can use this amplification. The amplification only, two important things. I can do amplification by applying the noisy operation n times, okay, in a row before measuring, okay? And then I cannot do this for absolute infinity. So there's an optimal n to use, which depends on the magnitude of the error, basically. How far is this from ideal gate or a unitary gate, okay, or an identity map in some sense, okay? So in a realistic situation, so a fidelity of good quantum computers would be, say, 99%, 0.99, yeah. Okay?
There were two ends, right? The number of times you read a circuit and the
Yeah.
number of
Shots.
the number
Yeah, let's define these. Yeah, so NS is the number of shots. This is the number of times I repeat. And little n, it's maybe an unfortunate notation, little n is the number of times I apply the operation before measuring. So I would run a circuit like this, prepare a row, and then apply lambda, 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 n times, okay, and then only measure at the end, okay? And I have to repeat this ns times, okay? So repetitions. Not repetitions, it's not a good name. Let's go, yeah, amplification, okay? So I've shown you how to reduce the error by 1 over n. And if let's think how much time it saves me, okay? I claim that it saves a lot of time, okay? So if my fidelity is around 99%, okay, I said n is around 100. How many shots did I save in terms of, suppose applying a gate doesn't take any time, it takes 0 time. Sorry? 1,000. 1,000 shots. Look, to reduce the error by a factor of 100, I need to increase the number of shots by 10 to the 4. So I reduced my time by 4 orders of magnitude just by applying this lambda n times in a row. Is this clear? So now, instead of taking 10 to the 5 seconds, it can take 10 seconds. The whole tomography, if I did this in this way, it would take 10 seconds, from 5 hours to 10 seconds. Okay, yeah.
So, okay, this works nicely because you have the tolerating channel. But how do you take a root of lambda?
A root of lambda.
I mean, no, you could apply the same idea to the general case.
Yeah.
Estimate lambda to this power n, and how do you get lambda from that?
Very good. So, in principle, I could do this because if I know how to multiply matrices, right, then applying lambda n times is just multiplying 16 by 16 matrices n times.
That direction is good, but backwards.
And then I would have to do some fitting. Okay, so I have to see exactly. So I have to obtain data. So this is something that goes by the name. I should maybe say this. So I wrote it for a very specific example, but what Robert is asking, what happens for a general lambda? Very legitimate question. For a general lambda, there's something that's called gate set tomography. Okay, it's a bit more complicated than what I just described here, but basically what it says, if you have a general lambda, okay, it's a 16 by 16 matrix, you can apply it n times. If you want to basically compute what is the expected for a given lambda, what you expect to see, you just need to multiply matrices. I know only how to multiply 1 by 1 matrices, but some computers know how to multiply bigger ones. So you can do this on a computer, and then you basically try to fit the data to lambda, okay? So it's some fitting procedure. Let's not get into it because it's a messy business, and there's a lot of very, very fine details in this, okay? But in principle, conceptually, it's possible, okay? And in fact, it is practical, okay? And again, it reduces, for this 2-qubit example, it reduces the computation time from the protocol time from 5 hours or something to 10 seconds. Okay? Yes.
So typically, would you have different eigenvalues for lambda matrix?
Yes, not only eigenvalues. I would have, it would be a full matrix. I would have to know all of. I wouldn't.
No, the power is the eigenvalues, right?
What?
When you raise it to a power, you.
So when I raise it to a power, it gets more complicated because when I raise it to a power, I don't know the diagonal form beforehand because I don't know the values. So I have to multiply matrices. I need to do some fitting procedure. Okay, I have to see. Basically, I have to fit. I have a matrix. I have parameters in this matrix. And this gives me what the model predicts for my expectation values, and I have my experimental expectation values, and I have to fit them somehow on the computer, crunch some numbers, and basically find the parameters of lambda. I'm not going to discuss how to do it because it's quite complicated. But in principle, it's doable. Yeah?
Are there any underlying assumptions that you made in order to kind of limit what we can practice?
So the limit is this. So, if I have a fidelity, basically, of the gate, the level of amplification I could do is always more or less 1 over the fidelity. So this would be the limit of amplification. But there's another limit. So then that goes back to your question over there. So I did 2 qubits. But what if I had 10 qubits or 100 qubits? Okay? How do I do? I mean, now lambda is a huge matrix, okay? 2 to the 100 by 2 to the, or 4, in fact, it's 4 to the 100 by 4 to the 100. How do I apply these matrices, multiply these matrices? I cannot compute what the model predicts. If I have lambda for 10, even for 4 qubits, in fact, okay, or these are very big matrices. I need to multiply them and then obtain the prediction for a set of parameters, obtain the prediction, and then fit them to the experiment. It's almost an impossible computation, classically. So the classical computation you would need in order to do this fitting procedure for this amplification, okay, for even a modest number of qubits is prohibitively large. So basically what we've traded the quantum process tomography was very simple. It does not require almost any computational power, basically inverting a matrix, okay? But it requires a lot of time for all these shots to get the statistical accuracy. Now I've traded it for very small QPU time, right? I took down 4 orders of magnitude, but now I have this monstrous computation problem, classical computation problem to compute the powers of this matrix lambda. Okay, which is not tractable beyond some very small number of qubits. Okay? Yes?
Sorry, isn't there another assumption about the state population knows? If you amplify it, then you're less sensitive to the state?
Yeah, there is. I'm not going to discuss it now. I'm going to discuss it later. Okay? There is another, what was mentioned here, which is correct, is that this amplification is also good because it also removes this issue of the spam errors. To see why, you note that when I'm amplifying here, the thing that's being amplified here is the description of the gate, not the preparation. The preparation and measurements are not amplified in this procedure. And if I take a large N, then the signal is composed mostly of this lambda and only a very small amount from the spam. So basically the spam part of the noise becomes negligible. So it becomes robust. We'll see this in a second in a more rigorous way. Okay, so this thing has 2 benefits. It's QPU time, QPU is quantum processing unit. So the time on the quantum computer is much faster. It's resilient to these spam errors, but it gives us a very difficult computational problem. Okay? Yeah.
So is this a technique that is actually experimentally implemented, so that feels like people just use randomized benchmarking?
Yes, it is.
So
Okay.
it's not-
Randomized benchmarking is good for some things, for example, to know the fidelity. And this technique is good when you actually want to know what exactly the errors are, okay? You want to know whether, for example, you've put too much power in your pulse and you over-rotated the there's an over-rotation in the gate, or there's many directions where these errors could go. For example, there's other issues. I mean, randomized benchmarking is not, I'm not going to discuss it maybe now, but randomized benchmarking is not sensitive to coherent errors, okay? I can explain why, but maybe not now. And this type of protocol is because you're just measuring directly the lambda, okay? So this is a much more sensitive protocol, but it is much more intensive in the computational power it requires once you try to do this for a group of qubits which is larger than 2, basically. Already for 2, it's because it's already quite a significant computational, classical computation, okay? So, okay. Now, really? No, but
50 minutes.
okay. I didn't even get to half of what I want to describe, but right. So now, okay, I just want to answer with this question because so I said this is a very difficult computational problem. Give me 5 minutes, okay? I said, but there is a good question that was asked: why would I ever need to compute lambda for a bunch of qubits, more than 2? Okay, because I use single 2-qubit gates. Why do I need lambda for more gates? The thing is that in many types of architectures, especially for superconducting qubits, when I'm applying gates, I'm applying them in parallel. Okay, so when I do an algorithm, you'll have a situation where the algorithm would, I don't know, all kinds of gates, but I will be applying many gates in parallel. And these gates also have, if I apply a gate on these 2 qubits, it actually does something bad to this neighboring qubit. So all in all, it's an operation that really involves all of these qubits together. It does have some structure, but I cannot think about it as a tensor product of operations. And then in order to basically know my lambda for this computational layer, okay, what happens at a cycle, right, the flop, basically, I need basically to describe a lambda which knows about all of the qubits. And that's what makes this simplification practically, very challenging for a large number of qubits, okay? So this is why I would need a model to describe the whole system, okay? This is one thing. Yes, other questions? So, yeah.
I think the advantage is there. I'm wondering if there is in the standard process tomography an additional information that you are using in your process, and maybe higher orders of the
Here?
Yeah, when you do your process, is this the exact same information as you get?
Oh, yeah, almost. There's some subtleties, but we discussed it. So, okay, let me just, before I conclude, so I've convinced you that amplification is good, but computationally, it's very difficult. But there is one way forward to maybe avoid this, to do amplification and avoid this very big classical computation overhead, okay? And that happens in the case where the noise channel is a very simple channel called a Pauli channel, okay? So maybe I should I just want to define it and then we can continue tomorrow. But the thing about the Pauli channel is that if my noise is composed of Pauli channels and my gates, my ideal gates, the gates without the errors are Clifford gates, then then computing any quantum circuit, any noisy quantum circuit, is a very easy thing to do classically. I don't need to multiply big matrices, okay? So a Pauli channel, okay, would be a channel that basically, in the cross representation, it looks like this. So it's kind of, there's always the P on the matrix on the right and the left are Paulis, and they're the same, okay? And so this is in this Pauli representation. And in the matrix representation, this is a diagonal matrix, okay? Lambda which would be 1, lambda A, lambda B, etc. And there is a connection between the lambda A's and the lambda B's, which I'll write down next time. But there is a connection between them, very simple connection. And the nice thing about it now that you see this is diagonal, okay? So if I want to know, if I have a Clifford gate, G, the Clifford gate G, what it does, it takes a Pauli to some other Pauli. That's it, to a Pauli string to another Pauli string, okay? And the lambda is diagonal. And then if I have basically a noisy operation, which is lambda and G, I can very easily know what, even if it's a very complicated noisy circuit, I could very easily know what, for any initial state, what is the output state. Okay, and that really allows me to remove this very difficult computational problem. The question is, I mean, this is not what happens in a quantum computer. How do we force the quantum computer to have these type of error channels? And there is a way to do that, and we'll discuss this tomorrow, okay? Okay.
I think someone mentioned it. Why doesn't one run lambda times lambda to the -1?
Because sometimes you want to know, you don't want to know the description of your quantum computer, but you want to know if you're not applying lambda. What you're trying to do is you're trying to apply the operation, a noisy operation, and then it's inverse. Yes. But what you get is not an identity operation. And then you could, it's some sort of benchmarking. You want to know how big is your noise in the system. With, so you apply some very complicated circuit, and then it's inverse. Then what's left is the noise basically describing the whole circuit. And then it's a very nice way to basically benchmark, what is the noise associated with the whole circuit, basically.
So I got confused. So it's a good idea or a bad idea?
It's a good idea to do a holistic, in order to do a holistic benchmarking of the computer. Somehow, what is the fidelity of applying a circuit on n qubits or for depth n on the computer? It's a good way to do that. Yeah. Which doesn't take into account any details of the noise.
Okay, there are no more questions. Let's thank Netanel.
כמה שאלות, רציתי...